All right, so this is lecture 24. Today is 5th of March, and we want to start the concept of friction. I always emphasize when it gets to this point, to covering the topic of friction, that the topic of friction is nothing new. In other words, let me put it this way. Static is all about analyzing rigid bodies or rigid body equilibrium, okay? And what we've done, we've looked at how to find external support reaction forces, okay? Which we did by drawing the free body diagram of the object, or internal forces, okay? Which we covered two cases, um, frames and trusses, okay? So topic of friction, although it is introduced at this end of the sort of the uh, course, and by the way, not only in this, not in all textbook, in fact, there's a good book by Hibbler that introduces the concept of friction early on. But anyway, what is friction? See, throughout studying this rigid body equilibrium, we have basically consistently said that if two objects are in contact or can slide with respect to one another, and this is sliding can be in different forms and shapes. You may have a roller that slides along a surface. You may have a color like this, a slider moves along an axis, and so on. All along, we assumed that there's only one force which is perpendicular to the direction of motion when it comes to drawing the free body diagram, okay? However, we have ignored something very important, and that is, in reality, there is no such a thing that this object can move freely, along this uh, surface. It depends on how rough this surface is. And that roughness means a force that is going to resist this motion, okay? At least it's going to resist it as you start applying a force in that direction. So the concept, in order to introduce this concept of friction, we need to, you know, discuss two things. One is that despite the earlier assumption, whenever two bodies are in contact and can slide against each other, okay, along the surface of contact, a force can develop that resists the sliding motion. Okay? That force is called force of friction. This is a very actually complex and very sophisticated force. But if you recall in physics, in order to describe or how to define or describe this force of friction, we introduced it through a very simple example. And that was, let's say you have an object sitting on the ground and you want to pull this object exerting a load P, okay, either sitting here or there's a roller between them, whatever, doesn't matter. This object has a weight. So when it comes to a free body diagram, obviously there is a vertical load vertically acting along the surface perpendicular to the surface of contact. Now, as you start moving, trying to move this object by exerting this force, in fact, in resistance to that, a force develops in the opposite direction that the potential motion is going to happen. And that's what we call force of friction. It is not as simple as this. It is not a single force. It is not only a function of one force, but and a parameter is actually a very complicated force, but we assume that this force or the value of this force varies like this. When you are applying a load, this force is going to increase as you increase load P increases, but this increase first is linear. Then as you increase it such that you keep on increasing it, then you get to a point that at that point this force slightly drops, and from that point on presumably stays constant. So there are two regions for that describing this force. This region is the force has increased the applied load, but the object still is not moving. We call this static region, okay, statics region. And we say that the force that develops this force is equal to a constant value times this normal force. And this is called coefficient of friction. Since static equilibrium exists, we call it static coefficient of friction. Then beyond that, as you further increase, a motion starts, and in this region, now you have motion. Still, we assume that the force that develops is related to this normal force through another coefficient, which we call that kinetic coefficient of friction. Okay? So, obviously, we only are dealing with this, or we want to keep the object in equilibrium so that everything we've learned, equations of equilibrium, still govern and are satisfied, right? So the types of problems, at least in this course, in dealing with friction come down to basically two types. So the type of problem you'll encounter are two types. One, explicitly, okay, stated in the problem that there is no motion. Of course, this statement may not come as explicit as that. You may say, okay, for instance, we don't want the object move, or should the equilibrium exist to find such and such values, okay? When this is the case, the maximum value that this force of static friction takes is mu s times n. And that is what we consider when the object is in equilibrium. But for the object to stay in equilibrium, this force should be less than or equal to this mu s times n, right? The second type of problems is we do not know, okay, if the object stays in equilibrium due to the action of the applied laws. And we want to verify equilibrium. So in this case, equilibrium, okay, is given. In this case, we want to verify. And this verification is what? For instance, we want to know if the forces applied have such and such value, okay, if equilibrium would stay, or find such and such values in such a way that equilibrium is still satisfied, okay? So what I would do, I would basically, instead of just going any further, I will do several problems for each of these two categories so you really get a good grasp of it. But let me tell you here that friction problems, okay, are nothing new, okay? They are similar to frame problems, except that a force that so far you have been ignoring, the force that develops as a result of the potential motion between two pieces in an object, you have to incorporate that. How do you incorporate it? Let's do a few problems. Okay, any questions so far? No? All right, so let's get on with it. All right, I will start with a simple example first. There's a guy weighs 180 pounds. Okay, he goes and buys a ladder. He wants to climb up that ladder to do something. I don't know, hang a picture on the wall or whatever. Okay, so lays the ladder against this wall where this guy is frictionless. The ladder has a length of 12 feet, but somehow he wants to reach very high on this wall. So he wants to go all the way to the top. It may sound crazy, but he wants to do it. Okay? So as an engineer, you're basically given the task that what is the minimum angle of alpha that is required to put this against the wall so that, okay, required to keep the ladder from sliding. Okay, the ladder has a weight of 30 pounds. Okay, this surface B is frictionless, but you have friction here, and the coefficient of static friction is given as zero point 0.1 or 0.5. For both cases, you want to do that. I will only do this one. Okay. So what is it that the problem is telling you? We do not want this ladder, despite the fact that this guy is standing way on the top, slide. Do not want the ladder slide. What does it mean? The ladder is in equilibrium. So this is problem type 1. We know that equilibrium holds. Okay? All right. So what do you do? It's a frame problem. It's a simple frame problem. the tools you have are what? Equations, free body diagram. So you draw the free body diagram. At this point, you have a 180-pound force. The only force you have here is a vertical load, that way perpendicular to the potential direction of motion. This angle is alpha. You have the weight of 30 pounds here. This is 12 feet. At this point, you do have also this vertical load, but if this ladder slides, would slide this way, so the force of friction that would develop would be in that direction. That is one thing which is very important and is different from, there are two things that makes these problems, although they are frame problems, but different, or you treat them differently. Number one is that when you draw the free body diagram, you have to, you should identify what direction this friction force is. Very simple. In order to find it, you say, okay, if this object potentially moves, what direction it's going to move? And the force of friction is always opposed to the direction of motion. That's it. This the other thing that makes these problems different, in that in many of these problems, you do not have to find all the unknown forces. You're asked specifically to find certain number of unknowns. Okay. With that said, okay, this is it. This is a free body diagram. Okay. We do know this F at A, which is a friction force, is keeping this in equilibrium. So if this is in equilibrium, the maximum force that may develop would be mu S times N at A. Okay. So let's, if this is the coefficient of friction, would be 0.5 NA. So you have three equations, three unknowns. What are the unknowns? NB, NA, and alpha. F of A is not an independent unknown because it is related to NA. So you have three unknowns, three equations. I will start with summation of forces along Y equal to 0. So you have NA minus 180 minus 30 equal to 0. So NA is 210 pounds, right? Summation of forces along X is equal to 0. You have FA minus NB, that's it, equal to 0, or 0.5 NA is equal to NB. This is 210. That'll give you NB is 105 pounds. Okay. One more equation of equilibrium. Summation of moments about A is, take that equal to 0. So what do you have? You have this force. If this is 12 feet, this would be 12 cosine alpha, and this would be 12 sine alpha. So you have NB positive times 12 cosine alpha minus 180 times 12 sine alpha, okay, minus 30 times 6 sine alpha. That's what this distance is. And that's it, equal to 0, okay? If you divide this, the two sides, by cosine alpha, okay, cosine alpha, cosine alpha, you get an NB, of course, is 105. So you get 12 times 105 minus, this would be tangent alpha, right? So minus tangent alpha times 12 times 180 plus 180 is equal to 0. Tangent alpha comes out to be 12 times 105 divided by 13 times 180, which becomes 7 over 13, and you get alpha is equal to 28.3. So in order for this ladder to stay in equilibrium, alpha should be 28.3, no more, no larger than that. If it is larger than that, okay, you'll see that this force is going to, the equilibrium will not be satisfied, okay? You can no longer, you cannot assume what you assumed here. Any question? Easy, huh? Very straightforward.
Will you move your paper up just a little bit?
Oh, sure. Here we go.
Thank you.
Many years ago, I remember this was given as a final exam problem. Okay, I'm going to do more problems of the first type. On Wednesday and Friday next week, we will do more problems, and I will send you even more friction problems with solutions since homework 10 is not due, or you don't need to turn that in. So this is another example. You have a device that acts as a brake mechanism, okay, like this. You have a rotating wheel or something supported here, and with the radius of this given as 0.15 meter. This disc is subjected to a torque of 5 Newton meter, so it is supposedly rotating. So you build this device as a way to, if needed, stop rotation. You want to know, okay, basically by exerting a vertical force P with your hand. There's friction at this point of contact of disc and this bar, and that's what, by pushing P, is supposed to stop the rotation. Coefficient of friction, static friction, is given as 0.3. So the problem, and let me give you all these dimensions, okay? This is 0.2 meters, this is 0.4 meters, and this distance that you need is 0.05 meters, okay? Now, the only problem is that you have only two choices, two possibilities. P can be either, okay, 30 Newton or 70 Newton, okay? You want to know which value of P can keep this wheel from rotating or keep this stationary. See, again, explicitly, I didn't say this is in equilibrium, but you want it to be in equilibrium, right? So you want to find the value of P such that the system is in equilibrium. So that is type number one. The way you solve the problem, identical to with the way you did frames. You have this piece, which is a disk, right? And then this piece, which is your brake mechanism. Draw their free body diagram. Let's start here. You have a load or moment applied, 5 Newton meter. There are two unknowns, OX, OY. At this point, if this was only like a roller at the point of contact, obviously you had this vertical load, but there's a friction here. You need to identify what direction that friction force it goes. This disk is moving in this direction, so friction force is always the opposite of that. So remember, this is a frame problem, so friction force on this disk is in that direction. Here would be in this direction. Same thing with NB. You have these two unknowns, AX, AY, and then this force P that you want to find, okay? So these are the two free body diagrams. And what is it that the problem is asking you to find P given that this is in equilibrium? A frame problem, right? The only thing is you have included this. So as I said, it is a frame problem except that you include now a force of friction between points of contacts. Number two, you do not have to find all the unknowns. Do not waste your time to find all the unknowns. Only focus on what the problem is asking you to find, which is P. So this is what I do. I will start with free body diagram number one. And in this one, all I do, I will try to find this force, this friction force, okay? And this force. So I take summation of moments about O is equal to 0, okay? What does that give me? These three go through point O, so you have negative FB times this distance, which is 0.15 plus 5 Newton meter equal to 0. So FB comes out to be 33.3 Newton. That's the friction force. Problem says that you want this to stay in equilibrium. That is, this force, which is the maximum friction force, okay, is mu times NB. This is given 0.3. So that will also give you NB, which is 33.3 divided by zero point 0.3 or 111.1 Newton. Okay? Any questions so far? All right. I don't care about OX and OY. I don't need them. I can find them, but I don't need them. Go to free body diagram number two. Take summation of moments about A is equal to 0. Because how many unknowns I have? 1, 2, 3. But this is the unknown that I want. So I just get rid of these other two. I don't care. I don't want them. Okay? So if you do that, okay, what do you have? P, which is a required P, required to keep this in equilibrium, times 0.6, okay, plus FB, which is 33.3 times this distance given, okay, 0.05 meters, 0.05, okay, negative NB, which is 111.1 times this distance, 0.2, okay, 0.2 is equal to 0. If you solve, you find the force that is required to keep this in equilibrium is 34.3 Newton. Okay, so you need a minimum force of 34 Newton to keep this in equilibrium. So if you are given two choices that you have to choose from to keep this in equilibrium, obviously the 30 Newton doesn't work. It's not enough. It's less than what is required, right? So then you have to choose 70 Newton to keep this in equilibrium. Any questions?
I had a question about the 5 Newton-meter moment.
Yes, which is given.
Yeah, how come it's only on one of the free body diagrams?
Oh, because I don't have it here. It is acting on this disk, right? And this disk is in contact here. So the only thing that disk does to this piece of the frame is due to the forces that develop between these two at this point. These forces develop as a result of this applied load, but that's all you have. So that's the free body diagram of that piece. It has taken into account that force implicitly because these two forces that are at the point of contact of this disk and this lever, right, are due to this load. But that's the free body diagram. Okay. Did I answer that?
Mhm.
Okay. All right. So let's do another problem. Okay. This is another problem of type 1. Let's say you have a guy who's trying to move an object, a crate. This crate has a mass of 150 kilogram, so its weight would be 150 times the gravitational acceleration g. So this guy, okay, is exerting, is standing, has attached a rope, a cable at an angle 30 degrees and trying to pull this crate at point C, and the guy is standing at point D, okay? Coefficient of friction between the crate and the floor is given, 0.3, and the coefficient of friction between this guy's shoes and the floor are also given as 0.4. And this guy weighs, its mass is 80 kilogram, so weighs 80 times G. What we want is, the problem is asking, determine if the man, okay, can pull the crate without slipping. In other words, this is what we need to do. Again, remember, without slipping. What does that mean? That means equilibrium. We want this guy stay safe, doesn't move. So we know this guy doesn't move, okay? This is a frame problem, has 3 pieces, the crate, the rope, and the man, right? So let's draw the free body diagram of all of these. This is the crate, this is the rope, and this is this poor guy, okay? So this guy weighs 80 times 9.8 Newton. And now we want to draw the free body diagram of each. This guy is not going to, we don't want this guy to slip. However, if this guy slip, in what direction this guy is going to slip? This way, right? Because that's how he's standing. So he's going to slip this way. So the friction force that would potentially develop would be in this direction. And you do have also a vertical load. So this is a free body diagram of this guy, okay? Then, of course, oh, I'm sorry, is pulling. So in other words, pulling this cable, so there's also this force of, I call that force P, which is acting on this cable. So this is going to be the free body diagram of the cable. And as far as this goes, the crate, if the crate moves, would move in what direction? This direction. So the friction force here, Fc, would be in that direction. You do have a vertical load here and the weight of 150 times 9.8. So these are the three free body diagrams. Let me label them. 1, 2, 3. Okay. Any questions? See, it is a frame problem. That's how you break it apart, draw the free body diagram. But I emphasize on two important things. One, identifying and include friction force and its direction. You cannot assume the direction. You need to make sure you have the correct direction. 2, do not find all the unknowns, only those you need. Okay, so let's go about it. Like any frame problem, I start with free body diagram number 1. This guy is trying to pull this. That is, the maximum force of friction that is resisting the motion before it starts, okay, is what? Mu s times n. That is the maximum force of friction. And since we don't want anything to move, yet we want the maximum force act on this or develop maximum friction force develops before it starts to move, that's what the value of the friction force would be, okay? So F of C is what? Is 0.3 times NC. Now, write some equations of equilibrium. You have summation of forces along y is equal to 0. So you have NC minus 150 times 9.8, okay? This angle is 30 degrees, okay? So you have plus P times sine of 30 degrees is equal to 0. If you break this into this component, this is the force along y. Also, you write summation of forces along x is equal to 0. So you have P cosine 30 minus FC is equal to 0, where FC was 0.3 NC. So you have two equations, two unknowns, NC and P, okay? You can solve for those and you will get, if you solve for them, P comes out to be 434.5 Newton, and C will come out to be 1,254.3 Newton from that free body diagram number 1. Free body diagram number 2 is a two-force member. So all it gives you is that this force is acting in these directions. So the force on this guy is acting in this direction. This is also 30 degrees. So let's go to this free body diagram number 3, the sky. Okay, remember mu is 0.4, and we do not want this guy to move. Okay, so what do? We just simply write summation of forces along x is well, actually, I will start summation of forces along y is equal to 0. Okay. So you have negative p, which is 434.5 cosine of 60, projection of this along y-axis, minus 80 times 9.8 plus nd is equal to 0. Those are all forces I have. This will give me nd that comes out to be 1002.04 Newton. Now, we want this guy not to move. In other words, we do not know what f of d is, right? I can find it by writing summation of forces along x equal to 0, assuming that this guy is in equilibrium, right? So you have Fd minus 434.5 cosine 30, okay? Those are the only two forces. That'll give me Fd is equal to 376.3 Newton, okay? So this is what comes out, okay? In other words, that is the force that is required to keep this guy in place. But he has these shoes, which have the coefficient of friction of 0.4. So what kind of friction force they generate, okay? The force that those generate would be 0.4 times NC, right? That is 400.8 Newton. So the forces that shoes generate, friction forces, are 400. For equilibrium purposes, all you need to keep this guy in equilibrium is a force of 376. In other words, for this guy to stay in equilibrium, doesn't slip, you need to have a friction force of 376. But the shoes can generate a maximum friction force of 400. And 400 is greater than 376. So the guy is going to stay safe. He's not going to slip.
Why did you use NC? Or
What
like
did I,
friction at point ND?
oh, did I use NC here?
Just for your like F equals 0.4.
Oh, I'm sorry. This is ND. I use this value here. Okay, that's the answer by using that. Yeah, I just put the wrong subscript. Thanks for noticing it. Any questions? So we will do more problems next week on Wednesday and Friday. You will, and I will send you a lot more problems, on friction, because that's an important topic. You will have it in the exam. And since you are not doing any homework, I need to load you with good example problems. But with that said, I hope you have at least some good understanding of friction, but I emphasize two types of problems. And the most important part is treat it like a frame problem, free body diagram. Just incorporate a new force that you have so far ignored.